In 1977, NASA launched 2 spacecraft on a mission to visit the outer planets. Nobody expected them to last more than a few years, but Voyager 1 and Voyager 2 kept going. Past Jupiter, past Saturn, past Uranus and Neptune. And then, instead of shutting down, they just kept flying into the darkness. 47 years later, both spacecraft are still transmitting. Voyager 1 is now over 170 astronomical units from Earth. That is more than 15 billion miles away. So far that the signals it sends, traveling at the speed of light, take over 22 hours to reach us. And what those signals have revealed about the edge of our solar system has shattered almost everything astronomers thought they knew. Because the edge of the solar system is not what anyone expected. It is not empty. It is not quiet. And it is full of objects, mysteries, and discoveries that have forced scientists to completely rethink how our cosmic neighborhood formed and what might be lurking out there in the darkness. For most of human history, the solar system ended at Saturn. That was the farthest planet visible to the naked eye. And for thousands of years, nobody had any reason to believe there was anything beyond it. Then came telescopes. William Herschel discovered Uranus in 1781. Neptune was found in 1846. Through mathematical prediction, French mathematician Urbain Le Verrier and English mathematician John Couch Adams both calculated where an 8th planet should be based on the strange wobbles in Uranus's orbit. When astronomers pointed their telescopes at the predicted location, there it was. Neptune's gravity had been tugging on Uranus in ways that could only be explained by another massive planet lurking farther out. But after Neptune, the trail went cold. Astronomers searched for decades for a 9th planet, convinced that something else must be out there. In 1930, a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona, finally found it. A tiny, faint point of light moving slowly against the background stars. They called it Pluto, named by an 11-year-old girl in Oxford, England, after the Roman god of the underworld. For 76 years, Pluto was the 9th planet, the edge of the solar system, the last outpost before the void. But here is the thing. Astronomers had suspected for decades that Pluto was not alone out there. As early as 1930, an astronomer named Frederick Leonard wondered whether Pluto might be just the first of many objects in a Trans-Neptunian population. He wrote about whether Pluto represented the first of a series of ultra-Neptunian bodies yet to be discovered. In 1943, Irish astronomer Kenneth Edgeworth proposed that a reservoir of icy bodies might exist beyond Neptune, remnants from the original cloud of material that formed the solar system. And in 1951, Dutch-American astronomer Gerard Kuiper published a landmark paper predicting an entire belt of frozen objects orbiting in the darkness past the planets. The problem was that nobody could find any of them. These hypothetical objects would be incredibly faint, reflecting only a tiny amount of sunlight from billions of miles away. They would be incredibly distant, requiring the most sensitive instruments to detect, and they would be moving incredibly slowly against the background stars, making them hard to distinguish from fixed points of light. The technology to detect them simply did not exist. That changed on August 30th, 1992. That night, 2 astronomers named David Jewett and Jane Liu were using the University of Hawaii's 2.2-meter telescope on Mauna Kea. They had been searching for Trans-Neptunian objects for 5 years, scanning the sky night after night, finding nothing. 5 years of pointing the telescope at dark patches of sky, taking long exposure images and comparing them frame by frame looking for anything that moved. Then they spotted something. A faint, reddish object drifting slowly against the stars. It was moving at just 3 arc-seconds per hour, which is almost imperceptibly slow. That sluggish motion told them it was very, very far away. They calculated its distance at roughly 44 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles, so this object was over 4 billion miles out, well beyond Neptune's orbit at 30 astronomical units. They had found the first confirmed Kuiper Belt object after Pluto. They wanted to nickname it Smiley, but it officially became known as 1990 2QB1. It was later given the official name Albion. The object measured roughly 200 to 250 kilometers across, a frozen world about the size of a medium asteroid, circling the Sun in the eternal darkness. Within 6 months, Jewett and Liu found 3 more objects. The floodgates had opened when they published their discovery in Nature in 1993. It confirmed what theorists had predicted for decades. There was indeed a third zone of the solar system beyond the planets, a belt of icy debris left over from planetary formation, orbiting silently in the cold. Today, astronomers have catalogued over 4,500 Trans-Neptunian objects, and they estimate that more than 100,000 Kuiper Belt objects, larger than 100 kilometers in diameter, are orbiting out there. Some estimates suggest millions of smaller objects populate this region. The Kuiper Belt is not a sparse scattering of debris. It is a crowded frontier. But finding these objects was just the beginning. The real surprises came when astronomers started studying them closely, because these frozen worlds turned out to be far stranger than anyone anticipated. Take Pluto itself. For decades, it was just a blurry dot in even the best telescopes. The Hubble Space Telescope could barely resolve any surface features. We knew almost nothing about it, except that it was small, about 2,300 kilometers across, cold with surface temperatures around minus 230 degrees Celsius, and had a moon called Charon that was discovered in 1978. Charon was unusually large compared to Pluto, about half its diameter, making them almost a double dwarf planet system. But what was Pluto actually like? What did its surface look like? Was it geologically active or dead? Nobody knew. Then NASA sent a spacecraft to visit. New Horizons launched on January 19th, 2006, at the fastest speed of any spacecraft in history. It left Earth at over 16 kilometers per second, so fast that it passed the moon's orbit in just 9 hours. Most Apollo missions took 3 days to cover that distance. New Horizons took a gravity assist from Jupiter in February 2007, picking up additional speed, and then spent 8 more years coasting toward Pluto. On July 14, 2015, at 11:49 Coordinated Universal Time, New Horizons flew within 12,500 kilometers of Pluto's surface. The spacecraft was traveling so fast, about 14 kilometers per second, that the entire flyby lasted only a few hours. But in that brief window, it captured the most detailed images and data ever collected of the dwarf planet. The images it sent back stunned the world. Pluto was not a dead, cratered ball of ice. It was geologically alive. The most striking feature was a massive heart-shaped region that scientists named Tombaugh Regio, after Clyde Tombaugh, who discovered Pluto. The left lobe of this heart turned out to be something extraordinary. They named it Sputnik Planitia, and it was a glacier of nitrogen ice over 1,000 kilometers across, and at least 2.5 to 4 kilometers thick. the largest glacier in the entire solar system. And this glacier showed no craters at all. In a solar system where everything gets pummeled by impacts over billions of years, a crater-free surface means the terrain is young. Geologically speaking, Sputnik Planitia is less than 10 million years old, probably much younger. Something is actively resurfacing it, erasing the evidence of impacts. The New Horizons team found convection cells in the ice, measuring 10 kilometers or more across. These polygonal patterns form when warmer material rises from below, spreads across the surface, cools, and sinks back down. Heat from Pluto's interior is escaping through the glacier, causing the ice to slowly churn and flow like a lava lamp in extreme slow motion. They found mountains of water ice. On Pluto, temperatures are so cold that water ice behaves like rock. It is frozen so hard that it does not deform under its own weight. These mountains rise up to 3,000 meters, comparable to the Rocky Mountains on Earth, and they appear to have formed relatively recently. They found possible cryovolcanoes. Wright Mons and Picard Mons are two enormous mounds that may have erupted slushy mixtures of water, ammonia, and nitrogen ice onto the surface. If confirmed, they would be among the largest volcanoes discovered anywhere in the outer solar system. They found a thin atmosphere of nitrogen with traces of methane and carbon monoxide, extending up to 200 kilometers above the surface. The atmosphere creates a blue-tinted haze similar to Earth's sky, caused by tiny hydrocarbon particles formed when sunlight breaks apart methane molecules. When New Horizons looked back at Pluto after the flyby, with the sun behind the dwarf planet, it captured images of this haze glowing in silhouette. It was hauntingly beautiful. The James Webb Space Telescope later observed Pluto's atmosphere in September 2202 and May 2023, revealing something found nowhere else in the solar system. The tiny haze particles control the atmosphere's entire heat balance through a unique mechanism. As the particles absorb sunlight, they warm up and rise. As they cool, they fall. This constant rising and falling regulates Pluto's atmospheric temperature in a way that has never been observed on any other world. Alan Stern, the mission's principal investigator from the Southwest Research Institute, said he never expected their encounter with Pluto to be shoulder to shoulder with the greatest discoveries in planetary science. He never expected to find an earth-shattering discovery about planet formation in the Kuiper Belt. And yet, they did. But Pluto was just one world among many. In 2003, a team led by astronomer Mike Brown at Caltech discovered an object even more massive than Pluto. They found it using the Samuel Oschin telescope at Palomar Observatory, scanning old survey images for anything that moved between exposures. The object had been photographed as early as October 21st, 2003, but the team did not realize what they had found until re-examining the data in 2005. When they calculated its size based on its brightness and distance, they realized they had a problem. The object, eventually named Eris, after the Greek goddess of discord, was 27% more massive than Pluto. It was farther from the Sun, currently about 96 astronomical units away, but at its closest approach, it comes within 38 astronomical units, similar to Pluto's distance. Its diameter is about 2,326 kilometers, slightly smaller than Pluto, but significantly denser. If Pluto was a planet, then Eris had to be a planet too. They had the same characteristics, just scaled differently. And if Eris was a planet, then what about all the other large objects being discovered in the Kuiper Belt? Were there 10 planets? 12? How many would they find? This is what forced the International Astronomical Union to redefine what a planet actually is. In August 2006, they created the category of dwarf planet. To be a full planet, an object had to orbit the Sun, have enough mass for gravity to make it roughly spherical, and have cleared its orbital neighborhood of other debris. Pluto and Eris met the first two criteria, but not the third. They shared their orbital space with thousands of other Kuiper Belt objects. Pluto was reclassified, not because it got smaller or changed in any way, but because astronomers finally realized how crowded the outer solar system really was. Pluto was not a planet among empty space. It was the largest known member of a vast population. Eris itself turned out to be remarkable. Its surface reflects 96% of the light that hits it, making it one of the brightest objects in the solar system. For comparison, fresh snow reflects about 80 to 90% of light. Eris is even more reflective. This suggests a surface of fresh ice, possibly nitrogen or methane, that has frozen out of a tenuous atmosphere. Eris orbits at a steep 44-degree angle to the plane where most planets travel, a highly inclined orbit that takes it far above and below the rest of the solar system. Its year lasts 557 Earth years. It has one known moon, Dysnomia, named after the goddess of lawlessness and Eris's daughter in Greek mythology. Then there is Haumea, which might be the strangest object in the Kuiper Belt. Haumea spins faster than any other large body in the solar system, completing one rotation every 3.9 hours. For comparison, Earth takes 24 hours to spin once. Jupiter, the fastest spinning planet, takes about 10 hours. Haumea does it in less than 4. This rapid spin has dramatic consequences. Haumea has been stretched into an elongated football shape by centrifugal force. It measures roughly 2,322 kilometers along its longest axis, but only 1,138 kilometers along its shortest. If you stood on Haumea, you would experience noticeably different gravity depending on where you were. At the ends, gravity would be stronger. At the middle, where the surface bulges outward from the spin, gravity would be weaker. Nobody knows exactly how Haumea came to spin so fast. The leading theory involves a massive collision early in the solar system's history. Another large object slammed into Proto-Haumea, blasting off material that eventually formed its two moons, Hihiaka and Namaka, and imparting the rapid spin that persists today. And in October 2017, astronomers discovered something even more unexpected. Haumea has a ring. During a stellar occultation, when Haumea passed in front of a distant star, as seen from Earth, observers detected brief dips in the starlight before and after the main occultation. These dips corresponded to a ring of debris about 70 kilometers wide, encircling the dwarf planet. No one had ever found a ring around a Trans-Neptunian object before. The discovery proved that ring systems are not limited to the giant planets. But Haumea's ring was not the only surprising ring discovery in the outer solar system. In 2023, the European Space Agency's CHEOPS mission observed the dwarf planet Quaoar passing in front of a distant star. What they found challenged theoretical models that had been accepted for decades. Quaoar has a ring system located at about 7.5 times the object's radius from its center. This is far beyond what scientists call the Roche limit, the distance at which gravitational tides from the parent body are strong enough to prevent orbiting material from clumping together. Inside the Roche limit, rings can exist because tidal forces keep the particles separated. Outside the Roche limit, particles should gravitationally attract each other and coalesce into moons. Quasars' rings are well outside this limit. By all theoretical predictions, they should not exist. They should have formed a moon long ago, but there they are, stable and orbiting, defying the models. Scientists are still working to understand how this is possible. One hypothesis involves the unusual shape or composition of the ring particles. Another suggests resonances with quasars' known moon, Weywatt, might stabilize the ring. But no definitive explanation has emerged. Makemake, discovered in March 2005, presented its own mystery. For years, it appeared to have no moons at all. That was strange, because almost every other large Kuiper Belt object has at least one satellite. The gravitational interactions during the chaotic early solar system should have given most large objects at least one companion. Then, in April 2015, the Hubble Space Telescope spotted something. A tiny, incredibly dark moon orbiting Makemake. The moon is charcoal black, reflecting only about 4% of the light that hits it. Meanwhile, Makemake's surface is bright and icy. This extreme contrast in reflectivity explains why the moon went undetected for so long. It was hiding in plain sight, too dark to see against the glare of its bright parent body. The moon's darkness raises questions about its origin. If it formed from the same material as Makemake, why is its surface so different? One possibility is that the moon is a captured object from elsewhere in the Kuiper Belt. Another is that some process has darkened its surface over time. Perhaps radiation-processed organic compounds or carbon-rich material that behaves differently than Makemake's icy exterior. Each of these worlds tells a different story about the conditions in the early solar system. They are like fossils, preserving evidence of events that happened over 4 billion years ago. But none of them prepared astronomers for what they found when they looked even farther out. Because beyond the Kuiper Belt, at distances so vast they are almost incomprehensible, astronomers started finding objects that should not exist where they are. On November 14, 2003, Mike Brown's team discovered an object that would become one of the most enigmatic in the entire solar system. They named it Sedna, after the Inuit goddess who dwells at the bottom of the Arctic Ocean in the coldest waters imaginable. And its orbit was unlike anything ever seen before. Sedna never comes closer than 76 astronomical units from the Sun. That is already 2.5 times farther than Neptune. Even at its closest approach, Sedna is far beyond the classical Kuiper Belt. But at its most distant point, Sedna swings out to an astonishing 937 astronomical units. That is nearly 100 times farther from the Sun than Earth. Its orbital period is over 11,400 years. The last time Sedna was at its current position in its orbit, human beings had not yet invented agriculture. The next time it reaches its closest approach to the Sun will be around the year 2076. It will then swing back out into the darkness and not return for another 11 millennia. The James Webb Space Telescope observed Sedna in 2223, revealing its surface composition for the first time. Scientists found ethane ice and complex organic molecules, but surprisingly, less methane than expected. This suggests Sedna's surface chemistry has been processed differently than other distant objects, perhaps by its unique orbital history that takes it through different radiation environments. Here is the problem. Neptune's gravity cannot reach far enough to have placed Sedna in this orbit. The Kuiper Belt exists because Neptune's gravitational influence shaped it. Neptune's gravity stirred up the primordial disk of material, scattered objects into various orbits, and continues to influence the region today. but Sedna's closest approach is more than twice Neptune's distance. At that range, Neptune's gravitational pull is negligible. So how did Sedna get there? Something else must have put it in that orbit. The possibilities include a passing star that came close to the Sun early in its history and gravitationally kicked Sedna outward, or an undiscovered massive planet in the outer solar system whose gravity shaped Sedna's orbit. Or perhaps Sedna was captured from another star system entirely, a visitor that became trapped by the Sun's gravity long ago. Mike Brown called Sedna a fossil record of the earliest solar system. Its orbit preserves evidence of some ancient gravitational interaction that we cannot directly observe any other way. And Sedna was not alone. In March 2014, astronomers Chad Trujillo and Scott Shepard announced the discovery of another extreme object. Its official designation was 2012 VP113, but they nicknamed it Biden because the designation contained the letters VP for Vice President. Its perihelion of 80.5 astronomical units was the largest known for any solar system object at the time. Even at its closest, it is farther from the Sun than Sedna ever gets. Then came the object discovered in October 2015 that was eventually named Leleakuhuna, a Hawaiian word meaning child who travels to distant lands. Its orbit reaches an estimated 2,100 to 2,800 astronomical units from the Sun at its farthest point. Its year lasts between 40,000 and 55,000 Earth years. These objects came to be called sednoids, after Sedna, which was the first discovered, and their orbits shared a peculiar feature that caught astronomers' attention. They all seemed to be clustered in the same region of space. Their perihelia, the points where they come closest to the Sun, were oriented in roughly the same direction. Their orbital planes were tilted at similar angles. The probability of this clustering occurring by chance seemed extremely low. Then, in July 2005, astronomers announced the discovery of another sednoid that complicated the picture. Designated 2023 KQ14 and nicknamed Ammonite, this object has a perihelion of about 66 astronomical units. But unlike the other sednoids, its longitude of perihelion points in the opposite direction. If the clustering of sednoid orbits is real and caused by a distant planet, this object suggests the gravitational dynamics are more complex than simple models predicted. In January 2016, two Caltech astronomers named Konstantin Batygin and Mike Brown published a paper that made headlines around the world. They proposed that the clustered orbits of these extreme trans-Neptunian objects could be explained by the gravitational influence of an undiscovered planet, not a small one. They were talking about a planet roughly 5 to 10 times the mass of Earth, a super-Earth or mini-Neptune, orbiting somewhere between 400 and 800 astronomical units from the Sun. Its orbital period would be between 10,000 and 20,000 years. It would be so far away and so faint that existing surveys had not found it. They called it Planet 9. The evidence was statistical. Objects with semi-major axes greater than 250 astronomical units showed clustering in multiple orbital parameters. Their longitudes of perihelion clustered around 318 degrees. Their longitudes of ascending node clustered around 113 degrees. Their orbital inclinations averaged about 20 degrees relative to the plane of the planets. The probability of this clustering occurring by chance was calculated at less than 0.07%. Until Planet 9 is caught on camera, it does not count as being real, Batygin acknowledged. All we have now is an echo, the shadow of a planet that we have not seen directly. inferred from the gravitational fingerprints it leaves on other objects. But that echo keeps getting louder. In April 2020, 4 Batygin and colleagues published new analysis in the astrophysical journal Letters, examining 17 Trans-Neptunian objects with orbits that cross Neptune's path. Using a different population of objects and different statistical methods, they concluded that the scenario where Planet 9 does not exist should be rejected at approximately 5 sigma confidence level. 5 sigma is the gold standard in physics. It means there is only a 1 in 3.5 million chance that the observed pattern is a statistical fluke. It is the same threshold used to confirm the discovery of the Higgs boson at the Large Hadron Collider. This outcome is the strongest statistical evidence yet that Planet 9 is really out there, Batygin stated. Not everyone agrees. The Outer Solar System Origins Survey, known as OSSOS, documented over 800 Trans-Neptunian objects using the Canada-France-Hawaii telescope. When the team carefully accounted for observational biases, meaning the limitations of where and when telescopes can actually observe, they found no statistically significant evidence for orbital clustering. Samantha Lawler, one of the OSSOS authors, stated that the Planet 9 hypothesis does not hold up to detailed observations. She pointed out that the original Planet 9 paper was based on only 14 objects, while OSSOS had characterized a much larger sample. The debate continues, but the search has narrowed significantly. Pan-STARRS surveys have ruled out about 78% of the predicted orbital region. If Planet 9 is as bright as models suggest, it should have been found by now in most of the predicted locations. Either it is fainter than expected in one of the remaining unsearched regions, or it does not exist. The Vera C. Rubin Observatory in Chile, which achieved first light in June 2205, is expected to settle the question. This new telescope will survey the entire southern sky repeatedly, detecting objects far fainter than previous surveys could see. Within 1 to 2 years of beginning full operations, it should either find Planet 9 or definitively rule out its existence in the predicted region. The observatory is expected to discover approximately 37,000 Trans-Neptunian objects, nearly 10 times the current census. We may have an answer very soon. But Planet 9, if it exists, is not the farthest thing astronomers have theorized about. That distinction belongs to something far more vast and far more mysterious. In 1950, a Dutch astronomer named Jan Oort was puzzling over a problem with comets. Long-period comets are those that take thousands or millions of years to complete one orbit around the Sun. Unlike short-period comets like Halley's, which return every 76 years and come from the Kuiper Belt, long-period comets appear to come from much farther away, and they arrive from all directions, not just from the flat plane where the planets orbit, but from above, below, and everywhere in between. Their orbits are randomly oriented in 3-dimensional space. They arrive continuously, century after century, an endless supply of icy visitors plunging toward the Sun. This created a paradox. Comets cannot have been orbiting the Sun since the solar system formed 4.5 billion years ago. The gravitational influences of passing stars would have disturbed their orbits, ejecting them from the solar system or pulling them away entirely. And comets lose material every time they pass close to the Sun. Their ices sublimate, forming the glowing coma and streaming tail that make them visible. Eventually, they burn out entirely, either disintegrating or becoming inactive rocky remnants. There had to be a reservoir somewhere, continuously replenishing the supply of new comets, a storage zone far from the Sun, where icy bodies could remain stable for billions of years, occasionally getting knocked loose and sent falling inward. Oort analyzed 46 comets observed between 1850 and 1952. He calculated their original orbits, tracing their paths backward to determine where they came from before entering the inner solar system. He found that their original orbits clustered around a distance of about 20,000 astronomical units from the Sun. He proposed that a vast spherical cloud of icy bodies surrounds our solar system at this incredible distance. Passing stars and the gravitational tide of the Milky Way galaxy occasionally disturb objects in this cloud, changing their orbits just enough to send them falling toward the inner solar system as comets. About 90% of observed long-period comets are thought to be injected into the inner solar system by these galactic tides rather than by passing stars. This became known as the Oort cloud. The numbers involved are almost impossible to grasp. The inner edge of the Oort cloud, sometimes called the Hills cloud, after physicist Jack Hills, who studied its dynamics, is estimated to begin around 2,000 to 5,000 astronomical units from the Sun. This inner region is thought to be shaped more like a disk or torus concentrated toward the plane of the planets. It may contain 2 to 5 times more mass than the outer cloud. The outer Oort cloud begins around 20,000 astronomical units and may extend to 100,000 astronomical units or more. That is roughly 3.2 light years from the Sun, about halfway to Proxima Centauri, the nearest star. The outer cloud is spherical, surrounding the solar system in all directions. For perspective, light from the Sun takes 8 minutes to reach Earth. It takes about 5 hours to reach Pluto. It would take over a year to reach the inner edge of the Oort cloud, and more than 16 months to reach its outer boundary. The Oort cloud is so vast that it occupies a significant fraction of the distance to the nearest neighboring star system. The cloud may contain over 1 trillion objects larger than 1 kilometer across, with a total mass estimated at around 5 Earth masses in the outer cloud alone. The inner cloud may contain significantly more. And here is the crucial point. No object has ever been directly observed at its location in the Oort cloud. We only see the comets after they have been perturbed into the inner solar system. The cloud itself remains entirely theoretical. It is supported by extremely strong evidence from comet orbits. Every time astronomers trace a long-period comet's path backward, it points to the Oort cloud region, but we have never actually seen an object sitting out there at 20,000 or 50,000 astronomical units, quietly orbiting in the darkness. We have found messengers from the Oort cloud. Comet C2014 UN-271, named Bernardinelli-Bernstein, after the astronomers Pedro Bernardinelli and Gary Bernstein, who discovered it, is the largest known Oort cloud comet. Its nucleus is approximately 137 kilometers across, plus or minus about 17 kilometers of uncertainty. That makes it roughly 10 times larger than a typical comet nucleus. The comet was discovered in dark energy survey data from 2014, though its true nature was not recognized until 2200. Its previous farthest point from the Sun reached approximately 40,400 astronomical units, placing it firmly in the outer Oort cloud. It may not have passed inside the orbit of Uranus in 4 billion years. It is essentially a pristine relic from the earliest days of the solar system, visiting the inner regions for perhaps the first time ever. As it approaches the Sun, reaching perihelion in January 2013, one at a distance of about 10.9 astronomical units just outside Saturn's orbit, telescopes have already detected activity. In June 2205, the ALMA radio telescope detected carbon monoxide jets erupting from its nucleus as ancient ices begin to sublimate for the first time in billions of years. But there is a difference between receiving visitors from a distant region and actually traveling there yourself. Which brings us back to Voyager. When the Voyager spacecraft were launched in 1977, their primary mission was to study Jupiter and Saturn. Voyager 2's trajectory was designed to also visit Uranus and Neptune, taking advantage of a rare planetary alignment that occurs only once every 175 years. The outer planets had lined up in a way that allowed a single spacecraft to visit all four giants using gravity assists, one planet's gravity flinging the probe toward the next. Nobody expected the Voyagers to keep operating long enough to reach the edge of the solar system. Their missions were planned to last 5 years, but the spacecraft proved remarkably durable. Their systems kept functioning. Their plutonium-powered radioisotope thermoelectric generators kept producing electricity year after year, declining slowly but steadily. By the 2000s, both Voyagers had traveled farther than any human-made object in history, and they were approaching a boundary that no spacecraft had ever crossed. The sun constantly blows a stream of charged particles in all directions. This solar wind carries the sun's magnetic field outward, creating a bubble around the solar system called the heliosphere. Inside this bubble, the sun's influence dominates. The plasma is solar plasma. The magnetic field is stretched solar magnetic field. But the sun is not alone in the galaxy. It is moving through the interstellar medium, the extremely thin gas and dust that fills the space between stars. Where the solar wind meets this interstellar material, there is a boundary. Actually, there are two boundaries. The termination shock is where the solar wind abruptly slows down from supersonic to subsonic speeds, slamming into the resistance of the interstellar medium like water hitting a wall. Beyond that is the heliosheath, a turbulent region of shocked solar wind. And beyond that is the heliopause, the actual edge of the sun's bubble, where solar plasma gives way to interstellar plasma. Before the Voyagers reached these boundaries, another spacecraft gave us our first hints of what lay ahead. In October 2009, NASA's Interstellar Boundary Explorer, known as IBEX, discovered something completely unexpected. A narrow ribbon of energetic neutral atoms was streaming from a specific direction in the sky, forming an arc across the heliosphere. This IBEX ribbon was not predicted by any model. Its existence revealed that the interaction between the heliosphere and the interstellar medium was far more complex than anyone had imagined. IBEX also confirmed something surprising. There is no bow shock upstream of the heliosphere. When the sun moves through the interstellar medium, astronomers expected it to create a shockwave in front, like a boat moving through water. But the sun is moving too slowly through the local interstellar cloud for a shock to form. Instead, there is just a gradual compression called a bow wave. In August 2012, Voyager 1 became the first human-made object to cross the heliopause. The spacecraft did not carry instruments specifically designed to detect this boundary. Its plasma analyzer had stopped working in 1980. But the plasma wave subsystem, which detects electric field oscillations in the surrounding plasma, provided the definitive evidence. On April 9, 2013, triggered by a coronal mass ejection from the sun that had erupted about a year earlier, the instrument detected vibrations in the surrounding plasma at approximately 2.6 kilohertz. This frequency told scientists the electron density around the spacecraft was about 0.08 electrons per cubic centimeter. That does not sound like much, and it is not. But inside the heliosphere, the electron density is only about 0.002 electrons per cubic centimeter. The plasma around Voyager 1 was suddenly 40 times denser than before. It had entered a completely different medium. We literally jumped out of our seats when we saw these oscillations in our data, said Don Gurnett, the plasma wave science team leader at the University of Iowa. They showed us that the spacecraft was in an entirely new region, comparable to what was expected in interstellar space, and totally different than in the solar bubble. Clearly, we had passed through the heliopause, which is the long hypothesized boundary between the solar plasma and the interstellar plasma. Working backward from the density measurement, scientists determined that Voyager 1 had crossed the heliopause on August 25, 2012, at a distance of about 121 astronomical units from the Sun. The formal announcement came on September 12, 2013. Ed Stone, the Voyager project scientist who has led the mission since its inception in 1972, announced we are in a new region of space where nothing has ever been before. Every day we look at data, we know we are looking at data that no one has seen before. Voyager 2 crossed the heliopause on November 5, 2018, at a distance of 119 astronomical units. The formal announcement came on December 10, 2018. The fact that both spacecraft crossed at similar distances, despite traveling in different directions, told scientists that the heliopause is roughly spherical, at least in those directions. But Voyager 2 had a crucial advantage. Its plasma science instrument was still functioning. This allowed the first direct measurements of interstellar plasma temperature, density, and flow. What the Voyagers found was not what scientists expected. For decades, the heliosphere had been depicted as comet-shaped. Astronomers imagined a rounded nose facing the direction the Sun travels through the galaxy, with a long tail streaming behind like a cosmic windsock. This made intuitive sense. The Sun is moving through the interstellar medium, so the interaction should create an asymmetric shape. Research published in Nature Astronomy in March 2200 by Merav Ofer of Boston University and colleagues revealed something completely different. Using data from the Voyagers, from the Cassini spacecraft, and from the New Horizons probe, they proposed that the heliosphere actually resembles what they called a deflated croissant, no long tail at all. Instead, two jets curl away from a central bulbous region, shaped by the escape of extremely hot pickup ions that had been detected by New Horizons. These ions are interstellar atoms that have been ionized by the solar wind and picked up by the Sun's magnetic field. They carry enormous amounts of energy, and when they escape rapidly beyond the termination shock, the whole heliosphere deflates. Because the pickup ions dominate the thermodynamics, everything is very spherical, Ofer explained. But because they leave the system very quickly beyond the termination shock, the whole heliosphere deflates. Another surprise came from the magnetic field measurements. Scientists expected the interstellar magnetic field to point in a significantly different direction than the Sun's stretched magnetic field. When Voyager crossed the boundary, the field direction should have rotated noticeably. It did not. The magnetic field changed by only about 2 degrees. Nature had not read the theorists' papers and did not know it was supposed to change the magnetic field direction, noted Tom Cremigis, the principal investigator for the low-energy charged particle experiment at Johns Hopkins Applied Physics Laboratory. The interstellar plasma itself measured between 30,000 and 50,000 Kelvin. That is surprisingly hot for the space between stars, far hotter than expected for undisturbed interstellar medium. This region is being heated and compressed by its interaction with the Sun's heliosphere, and the boundary itself was different for each spacecraft. Voyager 1's crossing took about 28 days and was messy, with plasma leaking back and forth across the boundary multiple times before the final transition. Voyager 2's crossing took less than 1 day, with a clean, sharp boundary. Then, in October 2020, both spacecraft detected something unexpected. The density of the interstellar medium around them began increasing. The space between the stars is not quiet, Oort observed. It is agitated and influenced by the Sun in ways we did not anticipate. Both Voyagers continue operating today, over 47 years after launch. Voyager 1 is now more than 170 astronomical units from Earth. Voyager 2 follows at about 142.5 astronomical units. Both spacecraft still operate 4 instruments: the cosmic ray subsystem, the low-energy charged particle detector, the magnetometer, and the plasma wave subsystem. Power from their plutonium generators continues to decline at roughly 4 watts per year. Engineers have been carefully managing the power budget, turning off heaters and non-essential systems to extend the mission as long as possible. Voyager 2's plasma science instrument was turned off in October 2024 to conserve power. Scientific instruments are expected to continue operating through approximately 22,005 or 22.6. Communication capability should last until approximately 2036. After that, the Voyagers will continue their journeys as silent ambassadors, carrying golden records with sounds and images of Earth, flying forever through the darkness. Voyager 1 will reach a distance of 1 light day from Earth in November 2006. That is the distance light travels in 24 hours. But even at over 17,000 miles per hour, it will take roughly 300 years to reach the inner edge of the Oort cloud, and approximately 30,000 years to pass completely through it. We have barely scratched the surface of what lies beyond. While the Voyagers were making their historic journey, another spacecraft mystery was playing out much closer to home, and its resolution would teach scientists an important lesson about jumping to conclusions. The twin Pioneer spacecraft, Pioneer 10 and Pioneer 11, were launched in 1972 and 1973, becoming the first human-made objects to travel through the asteroid belt and visit Jupiter. Pioneer 10 went on to become the first spacecraft to achieve escape velocity from the solar system. In the 1980s and 1990s, as engineers tracked the spacecraft's positions with extraordinary precision, they noticed something strange. Both Pioneers were slowing down slightly more than they should have been. After accounting for all known forces, there remained a tiny, unexplained acceleration, pushing them back toward the Sun. The effect was minuscule, about 8 times 10 to the negative 10th meters per second squared. That is roughly 1/10,000,000th of the gravity you feel on Earth's surface. But it was persistent and measurable. For over a decade, the Pioneer anomaly, as it became known, sparked speculation about new physics. Maybe Newton's laws broke down at large distances. Maybe there was dark matter in the solar system. Maybe our understanding of gravity needed revision. Then in June 2012, physicist Slava Turishev at the Jet Propulsion Laboratory and his team published the definitive answer in Physical Review Letters. They had recovered original mission data from boxes of magnetic tapes found under a staircase at JPL. Using this data and detailed thermal models of the spacecraft, they showed that the anomaly was caused by heat. The Pioneer spacecraft generated electricity from plutonium-powered radioisotope thermoelectric generators. These generators and the spacecraft's electronics produced heat that radiated away into space. But the radiation was not perfectly symmetric. Slightly more heat radiated from the front of the spacecraft than the back, creating a tiny but persistent push. When Turushev's team properly accounted for this anisotropic thermal radiation, the anomaly vanished. There was no new physics, no dark matter, no modification of gravity, just heat, pushing the spacecraft in ways that had not been fully modeled. The Pioneer anomaly became a cautionary tale. Even the strangest observations usually have natural explanations. You just have to look hard enough. But while our spacecraft slowly push outward, objects from outside our solar system have been racing inward to visit us. On October 19th, 2017, an astronomer named Robert Werik at the University of Hawaii discovered something that had never been seen before. Using the Pan-STARRS 1 telescope at Haleakala Observatory on Maui, he identified an object moving on a hyperbolic orbit. That meant its trajectory was not closed. It was not circling the sun in an ellipse like planets and asteroids and comets. Its orbital eccentricity exceeded 1, mathematically impossible for anything gravitationally bound to our star. This object had come from somewhere else entirely and was just passing through. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar. It became officially designated as 1I 2017 U1, with the 1I indicating the first interstellar object ever identified. The object was already leaving when discovered. It had passed its closest point to the Sun, called perihelion, on September 9th, 2017, coming within about 0.25 astronomical units of the Sun, closer than Mercury's orbit. By the time Werik spotted it, Oumuamua was already heading back out of the solar system. Astronomers had only 11 days to a few months of useful observations before it faded from view forever. Every major telescope that could observe it did. They gathered as much data as possible about this unprecedented visitor. What they found was deeply strange. Oumuamua's brightness varied by a factor of 10 as it tumbled through space. Every 7.3 hours, it would brighten dramatically, then fade, then brighten again. This extreme variation suggested an extremely elongated shape. If it was spherical, the brightness would stay constant as it rotated. The fact that it changed so much meant one dimension was much larger than the others. Initial estimates suggested a cigar shape, perhaps 10 times longer than it was wide, like a cosmic cucumber tumbling end over end. Later analysis suggested it might be more disc-shaped, like a pancake, which would also produce extreme brightness variations. Its surface appeared reddish, consistent with exposure to cosmic radiation over millions or billions of years. Cosmic rays bombard any object traveling through interstellar space, gradually altering the chemistry of the surface and producing a reddish tint. Size estimates range from about 25 to 400 meters along its longest dimension. Without knowing its exact shape, it was hard to pin down. The incoming velocity before it entered our solar system was approximately 26.4 kilometers per second relative to the Sun. Intriguingly, this velocity closely matched the local standard of rest, which is the average motion of stars in our galactic neighborhood. It was as if Oumuamua had been sitting relatively still in interstellar space, and the Sun had run into it. But the real mystery came when scientists analyzed its trajectory more carefully. As Oumuamua departed our solar system, it was accelerating faster than gravity alone could explain. The measured excess acceleration was about 4.92 times 10 to the negative 6th meters per second squared, with an uncertainty of about 0.16. That is roughly 1/1,000,000th of Earth's surface gravity. But it was definitely there, and it could not be explained by the gravitational pull of the sun or planets. This behavior is characteristic of comets. When a comet approaches the sun, its surface ices heat up and sublimate, turning directly from solid to gas. This gas jets away from the surface, and like a tiny rocket engine, it pushes the comet in the opposite direction. This is called outgassing, and it produces small but measurable non-gravitational acceleration. But Oumuamua showed no visible outgassing whatsoever. There was no coma, the fuzzy cloud of gas and dust that surrounds active comets. There was no tail. The Spitzer Space Telescope searched for heat signatures of dust and gas and found nothing above very tight limits. It looked like an asteroid, but moved like a comet. This paradox became the defining puzzle of the encounter. Several natural explanations emerged over the following years. In 2020, Yale astronomers Darryl Seligman and Greg Laughlin proposed that Oumuamua might be made of hydrogen ice. In 2021, researchers Stephen Desch and Alan Jackson at Arizona State University proposed it was a fragment of nitrogen ice from a Pluto-like exoplanet. Then, in March 2003, Jennifer Bergner at UC Berkeley and Darryl Seligman, now at Cornell, published in Nature what many scientists consider the most comprehensive natural explanation. They proposed that Oumuamua started its journey as a normal water ice comet in another star system. But during its long voyage through interstellar space, lasting perhaps hundreds of millions of years, cosmic rays penetrated tens of meters into the ice. Cosmic radiation breaks apart water molecules into hydrogen and oxygen. The oxygen recombines with other elements, but the hydrogen molecules get trapped in the ice structure. Over time, a significant fraction of the ice, perhaps up to 25%, gets converted into trapped molecular hydrogen. When this object approached our sun and started to warm up, the trapped hydrogen was released. This invisible hydrogen gas provided the thrust that accelerated Oumuamua without producing any detectable coma or tail. A comet traveling through the interstellar medium basically gets cooked by cosmic radiation, Seligman explained. It is just the most generic explanation, Bergner added. But not everyone was satisfied with natural explanations. Avi Loeb, who at the time was chair of Harvard's astronomy department, proposed an alternative that made international headlines. He suggested that Oumuamua might be artificial. Specifically, he proposed it could be a light sail, a thin piece of material designed to be pushed by starlight, perhaps a piece of debris from an alien civilization's technology. The question is, what is making it deviate from its expected path? Loeb explained. We have seen deviations of this magnitude in comets when they experience outgassing as ice is warmed by the sun, but there is no cometary tail around Oumuamua. So it occurred to me that this may be due to radiation pressure from the sun. The scientific community responded with significant skepticism. Jason Wright at Penn State, collaborating with Steve Desch and Sean Raymond, published a detailed analysis going through Loeb's arguments point by point. Under careful scrutiny, his claims were often incorrect, and there was little to no evidence that Oumuamua was an artificial object. By 22,000, astronomers had identified 14 other asteroids within our own solar system, showing similar behavior, accelerating without visible outgassing. These became known as dark comets, and Oumuamua appeared to be the first identified member of this class, rather than evidence of extraterrestrial technology. The second interstellar visitor arrived less than 2 years later and behaved very differently. On August 30th, 2019 Greenwich time, amateur astronomer Gennady Borisov in Crimea spotted an unusual object using a 0.65-meter telescope he had built himself. He noticed it was moving in a direction slightly different from typical asteroids. When professional astronomers calculated its orbit, they found an eccentricity of 3.356 and a hyperbolic excess velocity of 32 kilometers per second. This was not just unbound to the Sun. It was traveling so fast that the Sun's gravity barely curved its path at all. Unlike Oumuamua, this object looked completely normal. It had a visible coma, the fuzzy envelope of gas and dust that surrounds active comets. It had a dust tail. It was clearly outgassing, exactly like comets from our own solar system. Scientists named it Borisov in honor of its discoverer, and it became officially designated as 2I/Borisov, the second interstellar object. Because it was discovered while still approaching the Sun rather than already leaving, astronomers had months to study it. It reached perihelion on December 8, 2019, at a distance of about 2 astronomical units from the Sun, roughly the distance of the asteroid belt. What they found revealed that comet formation processes in other star systems are remarkably similar to our own. Observations with the ALMA radio telescope revealed unusually high concentrations of carbon monoxide in Borisov's coma, between 9 and 26 times higher than typical solar system comets at similar distances from the Sun. This suggested it formed in a colder region of its home planetary system than most of our comets. Polarimetric measurements showed unusually high polarization, indicating very primitive material that had never been significantly processed. The comet was also depleted in a molecule called diatomic carbon, or C2. This depletion is seen in comets that formed in the outer regions of their planetary systems, far from their parent stars. 2I Borisov gave us the first glimpse into the chemistry that shaped another planetary system, said Martin Kordener at NASA Goddard Space Flight Center. A third interstellar object was confirmed in August 2025, named 3I/Atlas. It was observed by the James Webb Space Telescope using its near-infrared spectrograph. The observations revealed a carbon dioxide-dominated coma with a carbon dioxide to water ratio of 7.6 plus or minus 0.3. This is among the highest ratios ever observed in any comet, solar system, or interstellar. Current estimates suggest about 1 interstellar object per year passes through the inner solar system, with roughly 10,000 such objects within Neptune's orbit at any given time. Most are too small and dark to detect, but improved surveys will find more. The European Space Agency's Comet Interceptor mission, scheduled for launch around 2028 or 2029 in partnership with the Japan Aerospace Exploration Agency, will wait at the Sun-Earth L2 point, about 1.5 million kilometers from Earth, until a suitable target is discovered. It will then race out to intercept it. If we are lucky, that target might be an interstellar visitor, giving us the close-up observations that Oumuamua's brief flyby denied us. The James Webb Space Telescope has produced perhaps the most revolutionary observations of outer solar system objects. In February 2025, researchers published results from the DISCO-TNO's program in Nature Astronomy. This was the first comprehensive compositional study of Trans-Neptunian objects using Webb's near-infrared spectrograph. They discovered that Kuiper Belt objects fall into 3 distinct classes based on their surface chemistry. The first class, which they called bowl type, is dominated by water ice absorption features, with carbon dioxide ice and silicate dust. These objects have the least red color, The second class, called double dip type, shows complex organic molecules, carbon dioxide ice, and carbon monoxide ice. Remarkably, these objects show pure carbon dioxide ice, something never before observed on any solar system body outside laboratory experiments. They have intermediate color. The third class, called cliff type, has the most complex organics, carbon dioxide and methanol. These are the reddest objects. Most remarkably, every object in the cold, classical Kuiper Belt belonged to the cliff category. The cold classical population consists of objects on stable, nearly circular, low-inclination orbits that have likely remained undisturbed since the solar system's formation. The fact that they all share the same compositional class suggests these categories are tied to where objects originally formed relative to the Sun. Webb also made unprecedented observations of Pluto's largest moon, Charon. Results published in Nature Communications in October 2024 detected carbon dioxide and hydrogen peroxide on Charon's surface for the first time. The hydrogen peroxide is particularly significant because it indicates active chemical processing driven by radiation and ultraviolet light from the Sun, even on a world where temperatures never climb above -200 degrees Celsius. Perhaps most surprisingly, Webb spectra of Eris and Makemake showed low deuterium to hydrogen ratios in surface methane. This is a signature of thermogenic methane, methane produced by ongoing or recent geological activity rather than delivered by comets or produced by ancient chemistry. The implication is that these objects, at the frozen edge of the solar system, may still have internal heat sources driving cryovolcanism or hydrothermal activity. The outer solar system is not a frozen static graveyard. It is dynamic, chemically active, and full of ongoing processes we are only beginning to understand. Scientists now believe the outer solar system was sculpted by a period of violent upheaval early in its history. The NICE model, first published in 2005 and named after the French city where it was developed, proposes that the giant planets formed in a much more compact configuration than they occupy today. According to this model, Jupiter and Saturn originally orbited closer together. As they interacted gravitationally with a disk of debris left over from planetary formation, they slowly migrated. Eventually, they crossed what is called a 2-to-1 mean motion resonance, where Jupiter completed exactly 2 orbits for every 1 orbit of Saturn. This resonance triggered an instability that sent shockwaves through the outer solar system. Neptune and Uranus were flung outward. Neptune plowed through the primordial Kuiper Belt, scattering objects in all directions. Some were thrown into the inner solar system, creating a period called the Late Heavy Bombardment that may have cratered the Moon and inner planets. Others were scattered outward into the scattered disk, and perhaps even the Oort cloud. The current preferred version of this model, developed by astronomer David Nesvorny, suggests the solar system may have originally had 5 giant planets instead of 4. During the instability, 1 ice giant was ejected entirely from the solar system, flung into interstellar space. We will never find it because it is no longer ours. This model explains many features of the outer solar system. It explains why Neptune's orbit is slightly eccentric. It explains why Pluto and other objects are trapped in orbital resonances with Neptune. It explains the structure of the Kuiper Belt, with its hot, excited population and its cold, undisturbed population. It explains how objects like Sedna could have been scattered into their extreme orbits. And yet, for all these discoveries, fundamental mysteries remain. Current estimates suggest we may still be missing about 10 objects comparable to Pluto in size orbiting somewhere in the outer solar system. The Vera-Rubin Observatory may find new dwarf planets the size of Pluto or larger, hiding in the darkness where no survey has yet been sensitive enough to find them. The sharp drop in object density beyond about 50 astronomical units, known as the Kuiper Cliff, has never been satisfactorily explained. Either something truncated the original disk of material during the solar system's formation, perhaps a close stellar encounter, or we simply have not looked deeply enough to see what lies beyond. The magnetic field direction mystery remains open. When both Voyagers crossed the heliopause, the magnetic field changed by only about 2 degrees when models predicted a significant rotation. We still do not understand why the interstellar magnetic field aligns so closely with the heliospheric field, and the Oort cloud remains theoretical. Despite being the best supported explanation for long-period comets, no object has ever been directly observed at its location. We see only the messengers, not the reservoir that sends them. What astronomers have found at the edge of the solar system over the past 3 decades has been nothing short of revolutionary. A third zone of the solar system went from theoretical prediction to populated frontier. Pluto transformed from a blurry dot into a geologically active world with nitrogen glaciers, water ice mountains, and blue skies. Dwarf planets with rings, extreme rotation rates, and possibly active interiors revealed themselves in the darkness beyond Neptune. Objects on 11,000-year orbits hinted at undiscovered planets or ancient gravitational encounters that shaped the early solar system. The boundary of the sun's influence turned out to have a shape no one predicted, deflated rather than comet-tailed, with plasma temperatures far hotter than expected. 2 Voyager spacecraft pushed through this boundary and continue transmitting from interstellar space, revealing conditions that challenge our models. Visitors from other star systems raced through our neighborhood, the strange and controversial Oumuamua, the more conventional comet Borisov, and the carbon dioxide-rich 3I Atlas, showing that material drifts between planetary systems throughout the galaxy. And the James Webb Space Telescope began revealing that even the coldest, most distant objects in our solar system are chemically complex and possibly still geologically active. The edge of the solar system was never really an edge at all. It was a frontier, and we have only begun to explore it. Every day that the Voyager spacecraft continue to transmit, they send back data that no one has seen before, from a region where nothing has ever been before. Every new Trans-Neptunian object discovered adds another data point to our understanding of how the outer solar system formed and evolved. Every observation from Webb or Rubin reveals complexity we did not expect. New Horizons, which flew past Pluto in 2015, continues operating in the Kuiper Belt. In January 2019, it flew past a small object called Arrokoth, formerly known as Ultima Thule, becoming the most distant planetary flyby in history at a distance of over 43 astronomical units. Arrokoth turned out to be a contact binary, 2 primordial bodies that gently merged billions of years ago, preserving evidence of the earliest stages of planetary formation. I never expected that our encounter with Arrokoth would be shoulder to shoulder with the Pluto flyby, Stern said after the encounter. The spacecraft continues heading outward, conducting observations of other Kuiper Belt objects from a distance and measuring the cosmic background light from its unique vantage point beyond most of the dust in the inner solar system. It has enough power to operate into the early 2030s. That spirit of exploration continues to define humanity's investigation of the outer solar system. The darkness is not empty. It is full of worlds waiting to be discovered, mysteries waiting to be solved, and answers we have not yet thought to seek. The edge keeps receding, and we keep following,